Okay, my great honor to introduce our speaker today, Professor Hwang from Stanford. I'm actually welcoming him back because he was here maybe a decade ago. Some of you were not here, and we're happy he could take time from his busy schedule to stop by. And the joke with him is today we have to use snow machine. We want to create that we're the feeling that we're in Canada. This is very strange weather, even though you grew up in the East Coast as well. So let me introduce him. He did his undergraduate at MIT and his graduate degrees at Princeton. And from there, he was at Bell Labs, where that's one of the premier places for condensed matter research and all kinds of other research labs, where he was a staff scientist. And after that, he went to Tokyo University, where he was faculty for about 7 years. In 2011, he came back to North America and became faculty at Stanford, where he's been since, and he's now affiliated with SLAC. So a little anecdote I can tell you about his work is, I've always been impressed because every time there's a breakthrough, in my opinion, it's not easy to have a breakthrough in this field. His name was always there. In fact, very recently, maybe a decade ago, he had a breakthrough about interfacial phenomena between oxides. His passions, a lot of his contributions has always been in complex oxide materials or transition oxides. And very recently, since he was very well versed in the discovery and understanding of copper oxides, he made a discovery, which I think is phenomenal, is superconductivity in the nickel oxide family, which is kind of isostructural to some of the copper oxides. But even if you ask theorists, they probably wouldn't have predicted 10 years ago you would find it in that. So I think it's a combination of deep intuition, intelligent endeavor that he makes these discoveries. They're not by accident, even though it's very hard to predict what you're going to find. So today he's going to share with us some of his latest progress, and I'm looking forward to see what he has to tell us. So let's welcome Harold.
Thanks very much for the kind and intimidating introduction. So I don't know if this will be entertaining, but I'll do my best. And at least for my preference, I welcome questions during. So just feel free to chime in. So yeah, I'd like to tell you a little bit of a funny interdisciplinary story that kind of mixes physics, chemistry, and material science together. So I'm coming to you from Stanford and SLAC. So since kind of one of the physical properties we're going to focus on is superconductivity, let me try to introduce this broadly. So it's actually quite a cool story. Turn of the previous century, Professor Onis in Leiden University was busy trying to liquefy lower and lower boiling point liquids, and was the first to be able to liquefy helium in large volumes. Right? And so kind of that ability to try to do first experiments in new phase space led to an underlying discovery for our field and our discussion today, namely superconductivity in mercury. So this liquid metal at room temperature solidifies and has a transition to dissipationless state right at 4.2 Kelvin. Right? So this is a very long time ago, 1911, but sometimes it's kind of hard to remember the context. So I put some of the kind of characteristic discoveries or dates in that vicinity, right? This is not very long after the discovery of the electron. The very first models of phenomenological approaches to thinking about electrical conductivity in solids, which is really basically a linear response relaxation model, was within a decade of this. And this is kind of early days or even before quantum mechanics per se, and certainly a quantum theory of solids. So that story is actually kind of interesting because some of the very basic questions continue to us today. So people knew that if I have a metal, the electrical conductivity gets better and better as you cool down over some temperature range. So there's kind of a very basic question: what happens in the zero temperature limit? Right? So one idea might be it's just going to get better and better and better all the way perhaps to perfect conductivity. Another possibility is actually I need thermal energy to be mobile. And then if I get cold enough, these things are going to freeze and localize. So my understanding is kind of in that context, some of these experiments were going on. These very basic questions about what happens to the ultimate fate of the metallic state in condensed matter. So a 1911 discovery in a good 50 years before this was kind of reasonably well understood. And a lot of this has to do with the fact that ultimately this is a macroscopic quantum mechanical phenomenon, and having the understanding and the tools to discuss this really took quite a bit of time. There's also very interesting developments experimentally to try to nail down some of the mechanisms. And so while there are lots of experiments I could tell you about, one of the key ones I can tell you about the development of these ideas was a so-called isotope effect. So people found that in many, but not all superconductors, if you could change the isotope, the square root of that mass times Tc is roughly constant, okay? And so that led a lot of people to really zoom in on saying that electron-phonon coupling, coupling to lattice vibrations must be important. And you can actually see that pretty simply in the sense that even the youngest among you, we've all solved this harmonic oscillator problem, right? The ball and spring oscillator. Okay? And keep in mind the resonant frequency associated with this is something that goes as square root of the spring constant over the mass. So if you say to me something is going with respect to the square root of the mass, this is the kind of thing you might think about. And even if you haven't seen this sort of thing, actually you can make a model, this is quite accurate actually, of the vibrations in a solid, in a crystal, by building up balls and springs, something like this. Right? So here again, as you could kind of imagine, this square root of mass is very important. Namely, this sets the slope of the sound waves, the acoustic sound waves in the system. So this was kind of one of the important steps. And just to give you a cartoon flavor of how you might think of the underlying microscopics of superconductivity, the notion is as follows. In vacuum, if I give you two electrons, we would think these are repulsively interacting. So it's kind of a strange situation. But one of the magical and interesting things that happens in a solid or in some medium is that you have very different time scales of response. And so a cartoon way you can think about this is an electron is shooting through your lattice. It's a metal. So Fermi velocity, the speed of this electron is very, very high. Let's say, you know, a tenth or a hundredth of the speed of light, that kind of scale. You know, the nuclei in your lattice are much, much heavier. So that response time, that inertial response is very slow. And so you could imagine that the electron shoots through, the lattice is kind of polarized or pushing around in response to this, but that first electron is long gone. And you have a second electron that nevertheless feels that attractive potential associated with that kind of delayed or retarded potential. Right? And so by this lattice medium, you can actually have a very interesting situation where there's a net electron attractive interaction that leads you to this new state where you can have perfect conductivity, for example. So this was a matter for the 1950s, and let's say we'll call them conventional superconductors, generally follow some version of this rubric. That is to say that the electrons interacting with the lattice and their vibrations is the microscopic mechanism underlying this superconducting state. And I should also say it's very useful. So my former colleague, Ted Jabal at Stanford, was one of the people that helped discover niobium-310. And if you or anybody you've known has ever done an MRI, right, a medical scan, it's using this material actually in the superconductor to do the imaging. So that's a very approximate and terse way to kind of introduce, let's say, conventional or understood superconductors. And of course, a lot of our community is interested in the things we don't understand. And so over the past few decades, there's been a lot of growing evidence and interest in systems that are quite diverse in terms of their materials origin. Organic systems, oxides, heavy fermion, et cetera, et cetera. You must have also have heard some of the recent developments in, let's say, van der Waals or twisted bilayer systems. This is kind of a class of materials that to varying degrees show superconductivity, but with enough qualitative differences that we think that the origin is fundamentally different from what I showed you previously. So common features of this is they're generally low-dimensional, quasi-two-dimensional states or explicitly 2D situations. Electron-electron interactions are very strong compared to what you would see in a typical metal or semiconductor. And they're often characterized by a dome of superconductivity that is a function of a tuning parameter. Can be pressure, you squeeze on the material, or it can be doping. You chemically dope this as you would in a semiconductor, right? And so it's a little bit hard to see perhaps, but all of these cartoons or phase diagrams exhibit a dome of superconductivity that's in proximity to a correlated phase, you know, often exhibiting some form of magnetism, antiferromagnetism, some density wave magnet, et cetera, et cetera. So in some cases, we kind of have very strong confidence that electron-phonon coupling can't be the dominant driving thing just because the scale of pairing and superconductivity is way too high to be understood from our understanding of those parameters. In other cases, it's less clear, but the general thinking is that rather than coupling to the lattice, these are situations where the electrons are pairing and interacting with each other with a manifestation of their strong interactions. Or a typical candidate is thinking about spin fluctuations as mediating that pairing, right? So very much an open question and the type of background in which we started to work on this problem. So let me drill down on one of these examples, namely the cuprates. Okay. So let me tell you a little bit about this specifically. This is a situation where I have a material, the so-called parent compound, where the electron-electron interactions are so high that we have an insulator, even though you might think it should be metallic. And one way you could think about this problem, this kind of circumstance often occurs when I have one electron at every site. So here's my cartoon of that. Right? And imagine a situation where the correlation's high, meaning it costs so much energy that I want to do whatever I can to make sure I don't have two electrons on the same site. So what can happen is you kind of have a traffic jam, and one ground state solution then is to keep each electron on individually on a single site. I have an insulator, and the remaining degrees of freedom I have are with respect to the spin degrees of freedom, right? And often that most low energy ground state is a so-called antiferromagnet, where each spin is oppositely aligned site to site. So this is the parent phase of cuprates. And it turns out then if I dope the system, for example, if I hole dope the system, which is to say I remove an electron here or there, it kind of unclogs this traffic jam. And so not only can we release kind of a metallic conducting state, a dome of superconductivity emerges, as first discovered in 1986 by Bednarz and Müller at IBM labs in Rüsselsheim. So what did we try to do? We tried to ask whether we could make materials that have a similar motif. Right? So I've tried to explain to you what this antiferromagnetic insulator is and where you find superconductivity. The question of what's essentially similar is a matter of opinion, right? We don't understand how superconductivity observes. You and I might have different opinions about what are the most central features, but that was kind of the motivating game, which is to try to mimic phenomenologically some of the starting circumstances. Okay, so looking at nickel is not profoundly shocking, I would say, right? It's next to copper on the periodic table. You could imagine generating materials or chemistry such that you could have the same type of configuration you would have in some of these cuprates. So skipping the details, if we could make a compound like this, so monovalent nickel, you would fill up the electrons across the d manifold of orbital states such that we're left with this one unpaired electron. And this would nominally look just like the cuprate problem. So the simple-minded thinking was that, if I could really make this kind of system, maybe this is a place where you would find superconductors, a new class of correlated materials. And this idea has been around apparently from the early days just after the discovery of cuprate superconductivity. And maybe the second or third paper theoretically in this series I just show you here, because it speaks to something we'll come back to here and there in the discussion today. Right? Title's rather suggestive. It says the infinite layer nickelate, this is this guy I'm talking about. Basic statement is actually nickel 1 plus is not going to be exactly like copper 2 plus. Right? And so what these guys did, they are computational theorists. They calculated the electronic band structure that they would expect. And they found basically two kind of parts of the Fermi surface. One is a large hole-like band, something that actually does look like the same thing qualitatively you say in the cuprate problem. They found these additional electron pockets, right? And we'll come back to these details. So at the level of this discussion, what I want to emphasize here is that there is something immediately and pre-understood that may be different. It is not just simply about a single band problem, but we might have this kind of interesting configuration. And so again, I'm reminding you that this is quite a long time ago. So this was a theory-led discussion at that time. So I think there's one or two of you from maybe materials and chemistry background, and and for the rest of you, if you're at all familiar with this, nickel 1 plus sounds kind of weird and crazy. And I picked up a version of the periodic table that emphasizes common oxidation states for these guys, right? So for example, in nickel, you can see nickel 2 plus, you see nickel 3 plus. You can't find nickel 1 plus as a typical oxidation state. And so you could immediately imagine from a variety of perspectives that this is a very strange material. It's not obvious to me or to us whether you can make it. And that's part of the story I'd like to tell you. Okay. So it turns out that the approaches we used are built on really creative chemistries built up over the past decades. And very loosely speaking, you can call them soft chemistry techniques, which let me loosely define as low temperature methods for chemical reactions or synthesis. The idea here is we're not using thermodynamic stability for growth. The idea is that you can get in regimes where you can use the topology of a starting crystal structure and slide things in and out. So intercalate or deintercalate species. And if you've ever played this game, this is a cartoon of that motif with this, right? So in some formalized sense, I can't shake up my blocks and expect this to be thermodynamically stable in any shape. But I can imagine a process by which I can make a well-ordered lattice. This is actually not that poor analogy of what we are doing here. As I said, we're building on some very interesting chemistry starting from the early 1980s. And so, as I said, we're trying to make something that, as far as we know, even today, is not formally thermodynamically stable. So there's no thermodynamic growth conditions I can go to expect to form this. And what these authors first found was the following rather interesting situation. They could grow something that is thermodynamically stable, initially in powder form, and they could use basically hydrogen or metal hydrides, basically very low oxygen chemical potential environments, to deintercalate first rows of oxygen and the other row of oxygen. So essentially pull out entire planes of oxygen to kind of collapse into this structure. Mm-hmm. And so that's kind of the thing we're going to do. And I will then just give you a picture or two of how this looks like. So like John, we've been long interested in oxide heterostructures. We are growing these structures by a specific version of pulse laser deposition. So we have a UHV chamber. We took this picture right at the moment where a high power UV laser has hit the target and flash evaporated a plume. For the past few decades, our community has been developing more and more precision techniques to be able to grow heterostructures like you might find in a semiconductor heterostructure laser or device but using these rather complex quantum materials. And here's an early example where we tried to grow one unit cell of one guy and a few unit cells of the other. This is actual transmission, electron microscopy data in cross-section for such a structure. So this is a little bit elaborate, expensive, that sort of thing. But the key next step after growing this structure is to do this deintercalation reaction. And it looks very modest, but this is super important, right? So this is a glass tube. These pebbles are giving me this kind of very reducing conditions. These are calcium hydride pebbles in here. We vacuum seal this in a tube for a few hours, cooked at something like 250 degrees C, right? So I showed you that there was literature from decades ago. So in terms of making the basic starting compound, it worked pretty well, but we could never dope them. And really the point of this slide is to say our first paper came out in 2019 and quite a few years of quite painful trial and error went into this. So it's thanks to Zhao and Denver that any of this got done, two postdocs that I had worked with at that time. Okay. So let me jump forward to what worked and start to tell you a little bit about what we know about the system. So we have been using thin films, and the reason we like to use thin films is for this project, especially the substrate is very essential for stabilizing the structure. So on the poster, I sent this picture where we start with this 3D nickel oxide and diagram us deintercalating these planes of oxygen. So we tried doping the system, and the very first hint of anything interesting happened around 2 a.m. Fall of 2018. At least in my lab, nothing interesting actually happens during business hours. So Denver made this very exciting discovery, but it was far from a real discovery in the sense that this was not a real zero resistance state. It was a little bit of a glitch. And again, I'm summarizing multi-man years of work or person years of work to try to get to the story I'm telling you. So this is an electron microscopy image of these early generation samples. If you don't really recognize what's going on, this is to say that 99% of the volume of the film was a complete mess. It had decomposed, fallen into secondary phases, et cetera, et cetera. And so we spent quite a bit of time trying to understand how to stabilize this, and finally got to a regime where we grow what ultimately turned out to be the superconducting phase in a narrow band, few nanometers off the substrate, right? So here we're starting to get real resistance zeros, right? A real signature of superconductivity. Now, what it turns out that happens is that the substrate is very important for essentially being a director. It kind of guides which plane of oxygen to deintercalate. And by breaking this degeneracy, there's a proximity effect where we can stabilize the right phase for a few nanometers. So kind of the ultimate structure that we can grow looks something like this. We have a heterostructure so we can gain these proximity effects on either side. And we're quite proud of this kind of a sample, which shows nominally a crystalline phase, which we know what we're measuring. And I'll give you some of the basic properties of this. But what's also true is that this is kind of the maximum thickness or volume film we can grow where we have complete control. It's not very big, right? You can see it's typically 10 to 15 nanometers. So one of our experimental challenges is how can we study what we need to study limited by this situation, right? I only give you 100, 150 angstroms thickness of some material, looks exciting, you know, how can we probe and understand it? So that's kind of what I'll tell you about. Okay, so the first story is after these materials development, we could finally confidently understand and publish a statement of the basic phenomenology. It's quite interesting. Again, we start with the thermodynamically stable phase. It's already pretty interesting. It's a kind of a well-known quantum material in and of itself. So in this particular case, this perovskite nickelate again, manifest strong electron interactions by going through this very big metal to insulator transition, where the insulating state is again characterized by a magnetic and orbitally ordered ground state. And it turns out that if you hole dope that lattice, again, you can suppress this ordering and make a metallic state, like the story I told you earlier. So now we do this interesting chemistry. We pull out these planes of oxygen, and so we go from O3 to O2. And what we find is that for the dope phase, we indeed undergo a superconducting transition. So this multi-decadal kind of suspicion or hope that nickel oxides might host similar kinds of superconductors, starts to bear fruit. So when I showed you that introduction to a large class of unusual superconductors, one of the things I showed you was they're often characterized by a dome of superconductivity. Right? So, we spent years wandering in the dark, but once we found something, there's lots to do. And certainly we found with different materials manifestations of this as a function of this turns out to be a hole doping axis, a generalized dome of superconductivity in this kind of parameter space. I should also hasten to add that around this time, lots of other groups came into this field and doing their own beautiful work using various, again, thin film growth techniques. Okay. So anyway, the message of this slide is that this is also at least has that phenomenology that I have a superconducting dome. This is a little bit of a jargon-filled slide, and so let me just focus on a few points. And some of this is for maybe the specialists in the audience, which is to say, again, our thinking was a lot about whether we can make an analogy to the high-temperature cuprate superconductors. And remember I showed you that funny theory title, right? Nickel 1+ is not copper 2+. And it kind of speaks to that issue that even though the starting ingredients, the orbitals, the electrons, and so forth are the same, we're at a very different kind of energy alignment. And so whereas in the kind of the cuprate problem, if I dope a hole in this antiferromagnetic insulator, you have this kind of very interesting situation where you have removed an electron with a lot of oxygen character. So again, jargon aside, we have a large kind of a body of evidence that this is a way to think about hole doping the system. And so labels aside, we have the same ingredients, but we're now one over on the periodic table, a lower oxidation state, and a lot of these orbital levels have aligned in a very different regime. And so the upshot of this is that we have a piece in terms of the electronic structure that looks very much like the cuprate problem. But we have an additional piece that is kind of a second electronic band or pathway. And so if I zoom out, the big picture question for our field is this second pathway important? If you say it is, then we have a fundamentally different and rather interesting problem. If you say it's a detail, then this is quite this kind of mapping scenario. I myself am not sure, but just to say this is kind of the way we're framing the discussion. And this is very much based on X-ray and electron energy loss spectroscopy performed by Matthias and Barrett in these papers, but I just give you this summary flavor. Okay, so let's go back again in my mind to these kind of starting characteristics. So we tried to mimic the cuprates. We found a dome of superconductivity. Another kind of a generic feature was a proximity to a magnetic instability. And so we could ask ourselves whether this system is magnetic. In terms of starting ingredients, those spectroscopies I showed you confirmed that this is a reasonable cartoon, that we have one unpaired electron on each site. But does this order? And again, one of the big challenges is how do you do these sorts of studies when you have such a tiny amount of material? And luckily, well, it's good to have friends. So I have friends that are really very good at resonant inelastic X-ray scattering. It's a technique that's really developed significantly over the last 2 decades, where you come in with an X-ray, typically at a synchrotron or a facility like that. A Raman-like process where you can probe things like magnetic excitations, right? And so this is very important for us to be able to probe what happens in these small volume samples. So what did we find? What I'm showing you here is kind of basic data along high symmetry directions of magnetic excitations in the system. So the first statement I would make is if you look at these red kind of peak position data points, it looks quite exactly like you would expect if you had spin wave excitations in an antiferromagnetic square lattice. So just in cartoon form, imagine that this was my ground state. Thinking about just like in the phonon problem, excitations of that spin lattice, this is the kind of thing you would see. And in fact, you could map this very much into a simple Magnon type of a problem with kind of near neighbor and next nearest neighbor interactions. We also studied for these antiferromagnetic correlations by using muon spin rotation. So the details aside, I should emphasize we did not prove, and nor do we have evidence that there's static long-range order, that we have this formal ordered antiferromagnetic phase. But what we did find is very strong and strongly damped magnetic excitations consistent with this underlying instability. Right? And this is quite a large energy scale. So these magnetic excitations extend up to 200 millielectron volts. Right? So it's quite a large energy scale where some people are thinking might be relevant for providing the coupling relevant for superconductivity in the system. Okay. So let me tell you that in some sense, why am I showing you there's very exotic experiments where you may say, well, the obvious thing to study initially is the electrical and magnetic properties. Anyway, our lab is very well equipped to do that. And it's been many years to be able to make real progress on this problem. And let me go back to this picture. So a couple slides ago, I bragged to you, look how hard we worked and look how beautiful our crystal is. So I'm going to take the same picture and say, well, actually, if you look carefully, there are a lot of crystalline defects, specifically extended defects highlighted by these yellow dotted lines. We think this is relevant because if you look at our work in the first few independent groups studying this problem, a lot of the things like the superconducting transition were common and quantitatively common across these samples. But things like resistivity, the electrical properties that we were so interested in, were bouncing around by a factor of 100, sample to sample, group to group. So it's kind of no way to make a living in trying to study this, right? And so our understanding was that these sorts of extended defects were dominating scattering. So electrons running through this material were being dominantly scattered by these crystalline defects. So again, back to a materials question, can we control them? I think I'm not pacing myself well, so I'm going to jump ahead and say just in cartoon form, two things. The reason these defects were forming wasn't, as far as I can see, because we weren't very good at growing this system. The reason that these defects were forming is while we're trying to use this substrate to stabilize this material and this transition, the lattice was changing by about 3%, which is actually a very big scale. And so we were actually forming these chemical defects to try to accommodate strain in the system. So to make a long story short, from that point of view, it's kind of a materials engineering problem. Are there better ways to distribute this strain? And let me just say, by moving to slightly different substrate in detailed conditions, hopefully you can see by this TEM image, something that's free of these extended defects. So after many years of work and many years after the initial discovery, we found a situation where we think we can start to first talk about intrinsic electrical and magneto transport properties of this system. And kind of not a surprise maybe to you is that if we go from this to this, a lot of things improve. First, the scale of the electrical resistivity drops way down, right? Less of these guys to scatter off of that I was telling you about. In fact, the superconducting transition goes to higher temperature. But more importantly, we think now that this is a very reproducible measurement and it has some physical significance. So let me just tell you one small piece of this. It just occurred to me, actually. This work was led by Kyo Lee, which is very pertinent and to this audience because he was a spectacular student that I worked with, but he's a graduate of this department a while back, right? So keep him coming, please. He's now a postdoc at MIT with Joe Chikelsky. But what was he able to show is by making these kind of deep advances in the materials fidelity, we could study then what the normal state electrical properties look like. There's a lot of detail here, but let me just say that firstly, at the peak of the superconducting dome, we found a very narrow region where the resistivity varies as temperature, linear in temperature in this kind of regime. And for the specialists out there, what was striking to us was that not just in qualitative form, but even in absolute magnitude, it was very similar to what you see in the cuprates. So these are various 214 cuprate single crystals, and you can see that the slope is almost the same. So as we dope from one side of the dome to the other, we find in the heavily overdoped side something that looks like a normal Fermi liquid metal. Namely, we see a resistivity that varies as T squared. And then the underdoped side, we have this characteristic logarithmic-like upturn. What's interesting is that possibly in this lecture room, you may have seen this kind of data for cuprates, for 2D systems. And so this is a very common motif that in the proximity of an unconventional superconductor, the normal state electrical properties from which it emerges often has this paradigm. And so it was very interesting to us to think about this in more detail. So again, let me skip those details, but just to say that these kind of very fundamental materials advances are allowing us to start to discuss intrinsic properties and think about a number of issues. I haven't gone through all of this, features in the Hall coefficient and other magnetotransport phenomenon. But you can kind of see that it seems like something weird is happening right where we have superconductivity, right? All lines are leading down. And again, this is pretty characteristic of a lot of these sorts of families of compounds. In other situations, it's often thought of as being driven by an underlying phase transition, a quantum phase transition between different phases on either side of the dome. We have yet to identify this. So it's suggestive, but it begs the question of what is the broken symmetry that might underlie that kind of interpretation of these studies. The second thing that we think these sorts of studies are helping us understand is that you and I and this person may have different ideas of what's driving superconductivity in the copper oxide systems. Now we have a very interesting situation where we can test some of these ideas and make a comparative statement. So two of the ones that we think we can say, again, maybe too much jargon here, but that, mod insulator, that correlated anti-fermion insulating parent compound does not appear to be a required fixed point or starting point for this phenomenology. We never have that. The second question would be the details of these orbital levels I was telling you about. Those fine details don't seem to be relevant for the basic appearance of superconductivity in this form. Okay. So there's lots going on, lots that we're trying to do. Maybe I was going to end with a few slides leading up to kind of preliminary results, which is another kind of important problem that we're trying to experimentally address. That is to say, if we can make some statement about what is the pairing symmetry of the superconducting state. Right? So if I go back to my introduction in your mind and say, these kind of lattice coupled superconductors, most of those are situations where you have a superconducting gap all the way around the Fermi surface, right? The entire Fermi surface gaps out. And this is a cartoon of that. As far as we understand from various kind of theoretical studies, at least there's the possibility that we have D-wave pairing in this nickelate system. So how would I think about that? This is a situation where the superconducting gap has this cloverleaf structure. So it's big over here, but it goes to 0 in these corner points. So the question is, can we make any experimental statement to try to decipher or discriminate between these two scenarios, which is rather important for making progress in our understanding of this. So the way we went after this problem is to try to measure the superfluid density. That is, what is the density of superconducting electrons running around in our system? And the way we did this was using a mutual inductance measurement. So imagine you have this little solenoid magnet on one side. You put an AC field, a magnetic field. What we're doing is basically seeing how much magnetic field gets through our narrow or sheet of superconductor. And it turns out that that mutual inductance measurement gives you a measurement proportional to this superconducting or superfluid density. Right? So this work was led by Shannon and Bai in our group. Okay. So what's the bottom line? Bottom line is, after a lot of work, basic measurement looks good. The red curve shows when I went to a resistance 0, and these blue curves essentially are proportional to that density of superconducting electrons, right? So indeed, where we go to the 0 resistance state, we can see the superfluid electron density come up. Now, the experiment we wanted to do was really in the low temperature limit. And the idea is follows. If I tell you that I have all my electrons in the 0 temperature limit going superconducting, and if I have a gap everywhere, then in order to kind of lose that electron density, I need to, or I would expect something like this red curve, something exponentially sensitive in temperature. But the funny situation is that if I have this kind of gap, so-called nodal gap structure, where I have parts of the Fermi surface that have vanishingly small gap, that tells me that even a tiny bit of temperature, I have thermal excitations that I can expect in the system, right? And so if you look in the low temperature limit of these two different cases, one can actually at least make an experimental statement about whether I have a node or not. And the bottom line is that we definitely seem to see a nodal gap structure. Now you can say, well, wait a minute, this one looks like the red exponential gap looks better. I don't have time to go into the details, but it turns out that this is a rather interesting situation where what we're seeing is a coupling of the superfluid with magnetic order on the neodymium site. We've actually got two kind of sublattices that are talking to each other. A very interesting problem that we're starting to work on. Okay. So let me just tell you where we are in order to try to get some advice from some of the experts here. So this is actual data, but just a cartoon of representative data. Again, we're following this improvement in the material science, and now we think we can do some very higher precision or accurate measurements. This is how it looks like. This is a measure of that superfluid density as a function of temperature. Again, we have this very funny low temperature feature associated with, we think, 4F moment ordering on the neodymium site. So there are some details that I'm going to skip in terms of the data analysis, but the big picture statement is the following. We have actually quite a low superfluid density. It's as if to say, you know, I measure how many electrons I have in my system in the normal state, only like 1% of them or something appear to be superconducting, few percent. Namely that the superfluid density is kind of small and on the order of TC. And I'm not doing justice to the ideas here, but let me give you, let's say we had a normal electron-phonon coupled, well-understood superconductor. And I tell you that in the zero temperature limit, all the electrons are going superconducting. And it kind of doesn't matter if TC is at 5 Kelvin or 10 Kelvin. If I go all the way to the low temperature limit, all the electrons are superconducting, right? But again, a characteristic of these sorts of materials is that that's not the case. And in fact, that the TC seems to scale with the apparent measures of the superfluid density. And a lot of the ideas that are longstanding about this kind of scenario is one where actually, if I think about describing the superconducting state in terms of an overall phase and an amplitude, it's not that the amplitude or the pairing strength is limiting us. It's that the fluctuations in the phase is really limiting TC, to give you a qualitative statement. Anyway, the last slide of this before I close out. So again, these ideas have come up in the context of these sorts of strange superconductors. You know, the cuprates are an example where it looks like, skip the details here, this is basically superfluid density scales in the underdope regime with the transition temperature. We don't find exactly the same behavior, but what I can say in a word is that we have this kind of square root of TC scaling. You can see our error bars are big, so you know the specialists don't have to take this too literally. But again, this funny situation where the scale of TC corresponds or correlates with the scale of the superfluid density. And we are inferring, therefore, that fluctuations in disorder are governing TC across the dome. Right? Okay, so where are we headed? So I actually told you a very small sliver of the material's phase space. Remember, I told you about growing a three-dimensional oxide, deintercalating oxygen planes, and making this infinite layer structure. What's cool is there's a whole bunch of different materials or chemistry themes. So you can make this guy, or you can make 3 of these guys, something else, 3 of these guys, 2. There's a whole bunch of like Legoland building blocks that you can find in this materials family. And similarly, you can relate that to these deintercalated structures. Now, this is work from far before superconductivity had been found anywhere. But we can ask ourselves, well, maybe it's more than getting lucky once, that there's a whole family of superconductors there. That's starting to appear to be the case in the sense that at least in the same kind of family of compounds, in the past year or 2 now, superconductivity has been found in a version of this material that has 5 of the layered building blocks that I've been telling you about, but a structure such that it kind of self-dopes one hole. Another version of this, a very different kind of electronic structure state. It's very early days, but if any of you are ever on archive, every day there's about 10 of these papers, it seems like, popping out. About 6 months ago, it was reported that, again, a very unexpected place to look. In this case, not the reduced form, but actually the oxidized form of this guy under very high pressure, so diamond anvil saw-like pressures. Above 12 gigapascal, there was indications of a superconducting state with a kind of a superconducting scale of order 80 Kelvin. So in fact, I was just at a virtual conference on Zoom for the last few days where lots of the people working on this were talking about this. So it's super early. But just to say that there are some indications that this isn't a one-off, but there are a family of nickel oxide-based compounds that has this kind of interesting problem. This is kind of a typical plot where if you aspire to have superconductivity at room temperature, this is your map of the world. But really, it's kind of, for me, a question of we don't really understand why these are superconducting, but we also don't understand what are the natural energy scales or cutoff scales for this problem. So it may saturate, it may grow, but it's an exciting time to try to sort this thing out. And so I hope I gave you a vague flavor of the types of things that we're doing in this problem. And so finally, I tried to highlight the young people that have been leading the different things that I told you about, but this has been a big endeavor with friends and collaborators all around the world. I won't read through them all, but super important to recognize their valuable collaborations. So let me close there and thank you for your time. Yeah.